Thank you all very much for coming tonight. This is quite a surprise. We started out a little over a year ago, our group, and when we were planning this event, we were wondering how are we going to get enough people to fill this auditorium so that we can demonstrate there's some interest in this concern. So we're real pleased with the turnout and glad that you all could make it. Now, we started about a year ago, a group of concerned citizens who observed the events that happened during the winter season at Plum Island and the houses falling in and all the emotional toll that took on people, and we thought there might be a better way to try to handle adaptation to sea level rise and the erosion that accompanies that, as well as all of the climate change issues. So we saw that sea level rise and storm surge are really a foothold to gain attention towards the bigger issue, which is climate change that's driving all of this weather and activity. And we'll talk some more about that tonight, but I wanted to first thank our primary sponsor, the Institution for Savings, because they give us a grant towards our educational efforts. And then the New England Grassroots Fund also stepped up to help us out and pay for some of our speaker expenses. And I'm not sure if you saw Richard, but Richard was working hard behind the scenes. And he came up with some really good oysters, I understand. Wolf Meadow Farm provided the cheese, and we thank them for that. And then our bar was stocked by Ipswich Ale Brewery, the Newburyport Brew Company, and also New England Wine and Spirits. And we wanted to thank Black Year Earth Compost. I have trouble with that logo. First I thought it was Black Bear, but anyway, we tried to make this a zero waste event, and we had a lot of people working really hard to make sure that everything would be recycled, including the shells. And then primarily I want to thank Lon Hockmeister, as he was the chairman of our event team for this event, and he took on a really big fish here. And I saw his task list, or the task list for this event, and we had a bunch of committee members, and his name was beside a lot of the tasks. So he really worked himself to death. And it's kind of funny what you can find on the internet when you Google somebody's name. I never knew that he was actually from royalty. I also, before I want to tell you that you can go downstairs and get 15% off of anything at Joe's after the program, but I also wanted to thank the event committee, and I'm sure they're all sitting in here somewhere. If you guys could all just stand up, if you're from Stormsurge, it helped put this all together, and give yourselves a round of applause. Thanks. Because this was really a team effort, and we have a diverse group of people with many different backgrounds, many different skills, and to have this kind of an effort, we can't all be scientists and technical people. There are got to be people that are good with computer skills, social skills, planning public events, and things like that. So I'm really thankful to everybody in the community outreach group and the people who decided to join the outreach team. There was a lot of work that went into this. Yeah, thanks. And then I just wanted to remind you, after the question and answer part of the program, if you submitted your email address, it's in a raffle, and we're giving away at least this big bottle of wine and a bottle of champagne, but I think there's a big food basket as well, or a gift certificate for that. So hang around if you've entered in that raffle. So our mission basically is to encourage and support our communities to prepare for the impacts of sea level rise, extreme weather events, and the effects of long-term climate change. And part of what we do is keeping the issue in the press, and so we have people who are writers as part of our group, and newspaper people who put articles or submit articles for the paper, and they get published, and it makes people aware of what's going on. We also had a number of university-level professors come and talk about various topics related to this. And we also featured a screening of the film Short Up, which was pretty moving. And Peter Phippen talked this fall, earlier in the year, in September, about the Sandy grant and how they were going to restore the marsh and make that more resilient and resistant to storm surge and storms. And then I just wanted to plug our next program, which is going to be held at the Newbury Elementary School. Erica Spanger-Siegfried, who I think is in our audience today, from the Union of Concerned Scientists, will be talking about a study that she has co-authored on how sea level rise is flooding coastal communities and how it's going to reshape our coast. So that's on the 19th of November at 7 p.m. Okay, so just a little bit about me. I have a diverse number of interests, and I've been a surfer since the age of 11, and that's really been one of my bigger passions and driving forces. I joined swim team because it would help me paddle. My son has sort of taken the same path. And I studied meteorology and oceanography not because I really loved the topics or that I decided I wanted a job in that field. I studied it because I needed to know how to forecast waves. But it gave me a lot of background in coastal geology and the processes that go on, and you learn about currents and learn how to identify them. And if you're going to be a surfer and go out in big waves, you also got to get back in, so you got to understand how that all works. And for the last 3 years, I was actually doing this a little bit on a professional level for this website and doing a daily surf forecast. Prior to that, my wife was a selectman for the town of Newbury back in 2007 when the erosion really started working down on Plum Island, and there was a lot of confusion. And so I basically took my camera, went down and took a lot of pictures, studied a lot of old nautical maps, and charted some changes and came up with the cycles of what goes on down there. So you can look at plumislanderosion.com if you want to learn more about that. And then if you know me, I also like really fast cars and I race cars. And I have a BMW service and performance business, and that's kind of my main line of work. All this other stuff is a hobby. But we get some cool cars in the pipeline that run on electricity, so that's all going to be pretty exciting. Now, way back in my career, back when I used to wear these kind of clothes, I was a planner for Anna Jake's Hospital, a healthcare planner. And so I got a master's in public health, so it's very strange that this whole climate change issue is drawing all of these fields together for me. And it is a major public health issue. There are going to be impacts from heat waves, because as our average global temperature goes up, if it's going to go up 5 or 8 degrees, you're still going to have, let's say, average 20, 30 degree winters. You're going to need 95 degree average days in the summer. So, you're going to see not like 5 or 10 90 degree days, but these 30, 40, 90 degree day summers are going to start arriving. And that's going to have impacts on health. Of course, there's going to be impacts from extreme weather, which I'll talk about shortly. Air quality is always an issue in our cities. Food and waterborne diseases, when we get a lot of rain and runoff and warmer conditions, there's going to be cross-contamination of water supplies with septic and public runoff. Certainly, I can speak to the tick-borne illnesses as a victim of Lyme disease myself. Ticks are basically expanding northward, and they're going to be crossing the Canadian border in not too many years, and they just used to never be around. As a kid, I used to play in the woods all the time. I've never picked a tick off me when I was a kid. Nowadays, you just walk in a field and you've got 10 or 20 of them on you. And of course, we all know about the West Nile, and then the drought and agricultural impacts that we're seeing out in California. So my goals for this presentation are basically to raise your sense of urgency to the challenges posed by what's going on. I want you to understand and think about what your personal vulnerabilities are relative to your business or your own home. And hopefully after you view this program and the other speakers tonight, you might be motivated to take action and convince some of your friends who didn't attend tonight to maybe do something. So just some quick reviews of what's going on with the planet. Not going to get too technical, but in case you didn't know, the greenhouse gases, basically the way they work, is they go up into the upper atmosphere and they act like a blanket over the Earth, and they don't allow as much of the solar radiation to radiate back out to space. That in turn starts to warm the atmosphere, and the oceans take up a lot of the heat. Where do the greenhouse gases come from? Well, in current times, it's coming from deforestation, the burning of organic materials, the products we use like aerosol cans, certainly from cars, trucks, planes, trains, and automobiles, and then also our manufacturing processes and some of the chemical processes that we employ. In the United States, this is basically where our carbon footprint comes from. A full third of it comes from the generation of electricity, and that comes from primarily burning coal and secondly natural gas. And there's been a big push on to get rid of all these coal-fired power plants because it certainly is a problematic fuel, and replace it with natural gas for an interim time period. And that'll get us a step in the right direction, but there needs to be some other sort of solution in there as well. But if you combine these two together, you see a full 60% of our carbon footprint is energy generation and transportation. And then the industry part of it is about another 20%, and some of that probably can't be altered too much. And then actually residential and business, I mean, that's basically heating oil and gas and that sort of thing, plus whatever we consume for products that contribute to the carbon footprint, and then agriculture is about 10%. So it's really up to us to be able to change how we consume energy, and we just need to start shutting off lights to start off with, unplugging your phones, or the chargers anyway, if there's no phone plugged into it. Do some recycling, walk, bike, and that sort of thing until some alternative energy sources become available. So if you look at all the graphs, basically global temperature roughly parallels the CO2 concentration, and really parallels it quite well when you look at 1850 on up to current time. And that really coincides with when we started burning fossil fuels. So fossil fuels are really driving this. And if we look at historical temperatures, now this goes back to 1900, you see that roughly the average global temperature came up about a degree in that period. And people always have questions about the climate models. They throw a lot of doubt into the climate models, and some states officially, like North Carolina, don't even want to acknowledge the climate models. But one of the things, if you understand modeling, and I look at weather models all the time and wave models, and if you're going to have an accurate model, and if you're a person who builds computer models, what you do is you build a model, and then you test it out on a known outcome, which is typically history. So if you knew what the temperature was back in the old days, and you've got your variables right feeding into this model, then the model should predict within an acceptable standard of deviation of statistical error what that temperature was. So when we put the climate models on that, you see that that black line running through the green line, it's right in there. It predicted historical temperature quite accurately. So what makes me nervous looking at this is that when we say, okay, so what if we just continue on as we are, keep oil in place, keep using coal, and don't change any of our habits relative to transportation and so forth, it just skyrockets. And so if the model is historically correct, then this is potentially what could happen. Now, if we really start ratcheting down and reducing our carbon footprint, and this is worldwide, not just us, so we got to get on the bandwagon and get everybody else as well, then we can temper it. But really, the effects of immediate action and drastic action really don't start to even show up until like 2050. So there's a certain amount of energy in this system that's rolling forward that has been put in there by our predecessors, our parents and grandparents and their parents. And so there's a certain amount of this already going on that can't be stopped. And of course, the sea level rise projections follow the temperature. And we have the high end of 6 feet by 2100, and this is relative to where sea level was in 1950. If we get down near the low end, we might be able to limit it to 3 feet. And really by 2025, we're going to see 8 inches. And it's not 8 inches on top of where it is now. It's 8 inches from 1950. But, we already got 6 inches. So that other couple inches is going to come. And, we keep setting records. And the other disturbing thing is that, we're not really throttling this thing back. Carbon dioxide is up to 400 parts per million at sort of a standard level now. And this is the first time this happened in 800,000 years. So when you look at the carbon dioxide levels, and you look at that red line, it jogs up and down, but it varies in like 50 to 100,000 year intervals. So you draw that line, and you see that skyrocket go from basically 150 parts per million to 400 in about 50 to 100 years. Normally that would take a couple 100,000 years to happen. So we humans have had a huge effect by burning fossil fuels and basically taking it out of the ground. The Earth took all of this. The other disturbing fact about all this is that if you look at the data, and if you look at the fossil record and you say, okay, where was sea level when we had this much heat and this much carbon in the atmosphere? Well, sea level was at least 21 feet higher than it is today. So basically what's happened is, it's sort of like at home, you turn your thermostat up and you wait for the heat to come on. It's not immediately 85 degrees. When you whack it up there, it's still 65 and creeping up. And this is what's happening with our ice sheets. They're melting, and the oceans are going to rise, and the oceans are going to expand, and there's going to be some sort of subsidence in some parts of the world. And so there's going to be some significant sea level rise coming. And part of the problem is predicting how fast it's going to come. The other thing that's happening is that the storms are becoming more intense. Now, this is only from 1950. The mid-latitudes and high-latitude storms, typically you might know as northeasters, have been increasing in frequency and in intensity. And then our precipitation events, the real heavy ones, are up by 71% here in the Northeast. And this data is all from the National Climate Assessment, which you can access online. It's pretty interactive and pretty easy to go through. And then I just want to bring in our 2012-13 storm season as an example of some extreme weather. Now, ever since the internet came up and the Navy declassified their wave models back in '96, I've been on the computer every day checking the wave models because I want to know when the surf's coming up. Am I going to take some days off from work in 7 days, or am I going to work? So, and then I also have access to all the weather buoys, and I go out there and I look at them, and I can see things in the buoys that the models don't see, and I get a really good estimation of what's going on at the beach. So what I saw in 5 storms in 2012-13, I had never seen in the 15 years I've been studying those models, and I'll show you why. So there wasn't a lot of snow or cold that year, but there was a ton of wave energy. In contrast to last winter, where we had a lot of cold and a lot of snow, but the wave energy was a fraction of that. So the way I look at this is, in my studies of Plum Island and watching what's happened down there, whenever we get waves of 10 feet or more, and they last for a long enough period of time, that's when we need to be concerned about erosion. So I took these storms and I broke them down. So we had Sandy, we had the northeaster that followed on her heels, and then in late December there was a blizzard. Then there was another big storm, Nemo, in February, and Saturn, which is the one that took all the houses on Plum Island in March. So if we start at the top with 10-foot wave duration. So Sandy was, it was a 2-day storm, 2.5 days. But the northeaster actually 41 hours and 3.5 tide cycles. And during that time, 10 hours, we're at 20 feet. Now, prior to, I'd see a storm, maybe a good one, hit 20 feet for an hour or two on the buoys, but to see it go to like 10 hours was pretty incredible to me. And then all the wave periods were fairly long, for what would you consider to be a northeaster. Typically, you see wave periods of 7, 8, maybe 9 seconds. Wave periods are an indication of wave power. If you're a surfer, you understand what that all means. So you go down to Saturn. Well, actually, let me stop with Nemo there. That was a 52-hour storm, 18 hours at 20 feet plus and 26 to 33 feet for 12 hours. So that was really huge. And then, of course, Saturn wasn't even close to us. Saturn went off the mid-Atlantic coast, was a monstrous storm, 700 miles wide. 72 hours of wave energy we got from that storm, 38 hours at over 20 feet, and that's why the beach gave up. So, in looking at storms, and I've seen a lot of them come and go. I was here for the storm of 78, I saw that, and I saw how that approached the shore, how it formed. I saw the perfect storm. And then there's the Mother's Day storm, the Patriots' Day storm, and then a whole bunch of others in between. And so I start thinking about all these different variables and characteristics of these storms, and basically said, at some point Mother Nature's going to roll the dice and she's going to get all these variables in a row, and we're going to get a bad case scenario. Now, I'm not talking about something of biblical proportions. I'm talking about coming up with a scenario of a storm that can realistically happen, because they already happen right now, and in a way that is not at all outside of the realm of possibility, especially given what's going on with climate change. So I got together with Robert Thompson. He's the meteorologist in charge at the National Weather Service in Taunton, and Lon Hochmeister, who's a physical oceanographer, and we came up with this scenario. I got all the pictures and the graphics, and we put together a story. So, what would be a bad case scenario? Well, we already talked about storms lasting 3 or 4 days. We know that that's bad because of the number of tide cycles that get going there. A retrograding approach, basically what that means is that the storms typically travel from southwest off to the northeast. That's your typical northeaster type of storm track. When we have a retrograding storm, what we mean is that the storm is actually traveling backwards off the ocean and riding up onto the mainland. And the reason that's dangerous is that it puts us in the strongest vector of winds and waves, and it also creates what's known as a traveling fetch, that as the storm moves along, it pushes the sea and the storm surge with it, so that when it makes landfall, all of that gets pushed up onto shore, and that's what happened with Sandy. A large and intense fetch off to the east-southeast, with a long duration would also be bad, because that's where all the ocean is. People think the ocean's off to the northeast, that's where all our waves come from, but if you're a surfer, you know that's not where your waves come from. It's only 150 miles off to the northeast before you hit Nova Scotia, but to the east, we see storm fetches of 1,000 miles or more sometimes. So I just want to talk a little bit about how we make big waves. You've got to have a lot of wind, you've got to have a lot of time, and you've got to have a lot of water over which the wind is blowing for that energy to get transferred from the storm to the backs of those little wind ripples that keep snowballing and getting bigger and bigger and bigger. If you have, for example, like a downdraft on a thunderstorm and it blows across Lake Winnipesaukee, it's only going to blow a mile, and it's only going to last 5 minutes, and you're not going to get anything for waves. So you need all of these mathematical factors coming together to make big waves. Sandy had big waves because wind fields started linking up in weather systems. So we had a storm that was already in existence before Sandy had formed, and had already started driving a swell in our direction. To the north was this big blocking high pressure cell, which was joining wind fields here and pushing that swell across. And then Sandy came up the coast and caught some of that and drove it in. So those waves were basically already formed, had big sails, and the wind from Sandy just re-energized them. And so we effectively had a 1,000-mile long fetch for the northern part of Sandy. And that's why Sandy was so devastating to the Long Island and Jersey shore. Another factor relative to swells coming from the east is that we've got a big gap in the continental shelf known as the Northeast Channel. It's 600 feet deep, and waves coming in through there don't feel the bottom until they hit Jeffrey's Ledge. Jeffrey's Ledge is sort of an underwater reef that breaks up a lot of wave energy. But when they come in from the east, they're coming in through deep water, and Jeffrey's doesn't slow them down that much. And then the last thing that would be a bad variable for a storm would be to have 10 inches of rain falling on a lot of frozen ground, because the water is just going to run off. It's not going to go anywhere. There's no trees with leaves and grass growing to suck up that water, and it's just going to all run off and create some flooding issues. So living along the coast, when we think of a storm threat, we think of hurricanes, certainly. And we also think of northeasters, which are extratropical low-pressure systems or mid-latitude lows. They call them cyclones sometimes. And if we look at hurricanes and you look at this graphic of landfalls, you can see, we're not really in their realm. We've certainly had a handful of them because New England sort of juts its chin out there into the Atlantic and catches these storms as they ride north. But really, if you're south of the Carolinas, you're going to see hurricanes, not so much up here. And if you look at the storm tracks, you see that we're really on the fringe of the storm tracks. So we're not out of the risk, but it's not really as big a risk. These guys, on the other hand, they form everywhere. They'll form as far south as Florida in the wintertime and ride up the coast. They form up between Europe and Greenland. They form all over the Atlantic, and they form much more frequently and easily than hurricanes do. And when you look at those storm tracks, we're right smack in the middle of those. So that's our risk. Now, the interesting thing about weather is if you listen to broadcast meteorologists, you only hear about what's coming from the west. Because once it's off the coast and away, you don't hear anything else. So you got to be a weather nerd, and you've got to follow this stuff. And this storm blew up back in 2007, and I was completely amazed about this. And I started getting phone calls from a friend down in Puerto Rico and said, Mike, what's going on with that storm up off of Nova Scotia? And so I say, well, why would somebody in Puerto Rico care about a storm up off of Nova Scotia? Well, this is what happened to the ocean surface. Now, that storm had 100-mile-an-hour winds, and it drove this huge swell on down to Puerto Rico. The only reason we didn't get that same type of wave energy is because that storm's fetch on the east side was hard up against the Canadian Maritimes, and so they acted like a breakwater for us. But that's what they got in Puerto Rico, 1,500 miles away. That storm, 250 miles to the southwest, would have delivered that to us. And so I'd say, wow, what a close call, and nobody even on the mainland even mentioned it, And of course, Sandy was another really close call. A few weather models had that thing tracking 4 hours further northeast and then making a left-hand turn. If that happened, we'd have been in this band of wind and waves up here. That would have been a problem. Okay, so why do we have storms to begin with? So basically what the Earth is trying to do, it's getting really hot at the equator, and it's cold at the poles, and it's constantly transporting this heat from the equator off to the poles, and the cold from the poles back down south, and where those air masses rub, we get storms. So it's part of the process of liberating heat from the equator in the tropics. And here you can see where it's hot versus where it's cold. So anyway, let's take a look at the 2013 tropical storm season and see how well hurricanes liberated heat from the ocean. So they forecast 16 storms. We actually got 13, so that forecast wasn't too bad. But where they were really off was on the number of hurricanes versus tropical storms. That was actually the exact opposite. And the reason that happened was because we had unfavorable weather. The sun was still shining and the ocean still got hot, but there was a lot of African dust and wind shear, so the storms just didn't form. And I want to talk a little bit about this ACE index. It's the Accumulated Cyclone Energy Index, and basically it's a measure of storm energy and longevity totaled across the hurricane season. So if you have a lot of intense storms and they last for a long time, you get a high ACE score, and if you don't, then you get a low ACE score. So the ACE score for 2013 was like 33, and you can see the average is up around 100. And 2014 was kind of right on par with that. Fewer storms even, but just nothing happening until Gonzalo brought it up to 65 for 2014 thus far. So you get asked the question, where did all that heat energy go? Well, there's other things out there like satellites that measure water temperature all over the globe. And they produce this graphic, and that's what's known as a sea surface temperature anomaly. And what that is how much warmer the ocean was back in December of 2013 versus what it should have been. So the world's oceans were pretty much 3 to 5 degrees Fahrenheit warmer than what they historically should have been. And 3 to 5 degrees doesn't sound like a lot of temperature difference, but when you try to heat an ocean of that size, imagine the electric bill if you had a swimming pool that big that you try to raise 5 degrees. So there's a ton of heat energy stored in the ocean, and that's what's happening with climate change, is that the air isn't warming as quickly as you would think because the oceans are sucking all the heat out of the atmosphere, and it's actually stabilizing our climate by absorbing the heat. But it's also creating changes in the ocean, which I won't get into in this presentation. So what happens when you park warm water up near the poles where it's cold and dark in December? You get a monster storm. And the way the jet stream ran last winter, Europe got pounded by probably 4 or 5 storms, almost the size of Sandy. And what I want to do is kind of bring you down to ground level eventually. That previous picture was a satellite photo, but that storm basically took up the expanse between England, Spain, Portugal, all the way over to Newfoundland. And the fetch to that storm started up near the ice pack in Greenland up there and made this huge swath of 50-foot plus waves heading for Europe. Now, if you look at what that did to the ocean and compare that to the United States, I mean, you've got 30-foot wave heights and more, about 75% of the size of the United States. That's a huge amount of energy being unwound there. So I'm going to take you down to ground level. We're going to start in the Azores and show you what 30 to 50-foot waves look like. Now, the Azores are a volcanic rocky island. They can sustain this type of abuse, and they've seen something like this in the past, and you don't have any houses sitting right on the water there for reasons like this. But those waves are gigantic, and they had periods of 25 seconds. So when you have a 50-foot wave with a period of 25 seconds, when that wave breaks, it actually lifts the swell out of the water. The bottom forces the swell up, and you typically will get a 90 or 100-foot breaking wave when you have a 50-foot swell with a period like that. There's a pier underneath that 20-foot crane there made out of cement. And now we move to Portugal, and we're standing on top of a 90-foot cliff looking down on what was probably a 75-foot wave that broke there. And here are those 90-foot cliffs with like a 50-foot basilica up on top. The rock outcropping down the bottom here is about 20 feet tall. There's just some crazy wave energy being unleashed there. And you can see people up on the cliff there. You don't want to get too close to the edge. And then we move over to England. And I got to tell you, I didn't Photoshop anything here. This is all real. And this is happening in our ocean. This is in the Atlantic. We're not talking about some super typhoon out in the Southwest Pacific. This is, in our ballpark. Now that's a big wave. Now what happened in England was they had a huge amount of storm surge inundation. There's a lot of flat land there, and hundreds upon hundreds of acres of farmland were inundated by salt water. And we had codfish on golf courses and seals in people's backyards. So how did rock structures fare? I mean, that's what mankind likes, right? If we want to keep something out or in, we build a wall. Build a Berlin Wall to keep the people in, keep a seawall to keep the ocean out. And our favorite material for construction is rocks or cement, which is our man-made rock. So how did rock structures fare from this storm? So in the Azores, they have roads running along the coastline, and they've got mortared seawalls all the way along there. Those things were hammered and torn apart. Rocks of 200, 300, 400 pounds were pulled off the ocean bottom and hurled over seawalls and onto roads. That's why the stones in the jetty are huge. I don't know if you saw them building that, but when they come down 95, they could only fit 3 rocks on a tractor-trailer flatbed because that's how big they need to be so that waves don't lift them up and throw them. they still get moved around. That's why the jetty falls into disrepair after 20 years. So the ocean's got a lot of energy and a lot of force. So here's this cliff stack in Dorset, England, before Hercules, that storm. Here it is afterwards. Then in Port Cawthon Bay was this nice sandy beach, and they had this rock arch. A lot of people take pictures of that, and there's postcards of it. You notice that the beach went away and the rock arch is gone. That's the power of water, and that's something that, as a surfer, I have an inkling of it, because I've been in some, I haven't been in 20-foot waves, but probably 15 feet anyway, and you take quite a thrashing. So I can't imagine what 50 to 100 feet is like. I mean, I see these guys, riding jet skis and getting towed into that stuff, but I think a lot of them are very fortunate that they make it. So what ingredients are necessary to make a storm like this? So storms really like contrast. So we have, cold air up here in the Arctic, and we've got this warm Gulf Stream and tropical air down there, and when these two air masses get together, we have problems. And basically the way that works is cold air is really heavy and dense. It moves right along the surface, and it sort of plows underneath the warm air mass. The warm air rises, cools down, the moisture in the air forms clouds, and as that warm air rises really quickly, it creates low pressure along the surface, and we start to get a storm. The other thing storms really like is this Gulf Stream that runs along our coast, because there we have 70-degree water in the middle of winter sitting out off our shore. And so you get a cold air mass that pushes in off of Canada and out over that, and you're going to get a storm forming. It's a high-octane moisture feed. Storms also like to form underneath a wavy jet stream, and when the polar and tropical jets merge. So let's just talk a minute about jet streams. So basically they're fast-moving rivers of air high in the atmosphere, and it's going to tell me I can't play another video. So we'll skip that. But anyway, you have two jets that we're concerned about here in New England. We've got the polar jet to the north that separates the polar air from the temperate regions, and then the subtropical jet that separates the tropics from those temperate mid-latitude areas. And generally, they travel around the globe. There's a little bit of waveforms that travel through them, and they shuttle weather systems along. And we'll skip this. So here's a graphic of a jet stream in a warming climate. So we used to have this jet stream that would have what we'd call a zonal flow, kind of flowing in a slightly, in a much less wavier form, pretty much right across the northern part of the continent. Weather systems move in and out in the day. But in a warming climate, what happens is the jet gets all distorted and undulated, and it starts to have these areas where it really runs and then it slows down, and it really runs and then it slows down, and then other parts are, dips way down and gets really slow. When a storm forms, it likes to form in these high amplitude troughs. So what you get is divergence in that part of the jet stream when the jet is running really strong, and that'll typically precipitate a big storm. In this case here, a storm forming here would run fairly quickly off to the northeast because the jet's moving fast. But I'll talk a little bit about weather systems stalling. If you want to learn more about how this jet is affected by the warming climate, you might want to look up Jennifer Francis on YouTube. She's got a presentation there that talks about this. So let's talk a little bit about the polar vortex. So we had this big dip in the jet stream. So that's why we had all that snow, because these storms kept riding up north along the coast, dumping a bunch of snow. And so we had all of this cold air all the way down into the south and also New England. But up in Alaska, they were enjoying 50-degree weather. And then, of course, California had the big drought. But this is more the normal type of jet stream that you would see. But this type of high amplitude setup is what you're going to see in a warming climate. And of course, when you run warm air all the way up here, look, now you're bringing your contrasts very high to the north where it's really cold as well. So the other thing that happens when these jet streams, when they start changing their speed and undulating, is that they cause storms to stall or retrograde. So how often does that really happen? And I started paying attention to this a little bit more because I had this presentation coming up, and I watched this storm stall for 10 days over the Azores. There was a gale center. Imagine a storm blowing from the east for 10 days on Plum Island. There wouldn't be anything left. I never saw that happen before. Then just recently, back in early October, we had a couple of tropical systems, or the remnants of those, come together and make for another big, monstrous storm out over the open ocean. The jet stream was doing some crazy nonsense here, but here's where the storm formed, and then the jet stopped. And there we are, just in terms of reference. And what we got was another one of these big cyclones out over the open Atlantic. It sat there for 4 days. Fortunately, didn't impact any land masses and just kind of spun itself out. But, you know, a big storm. Spain over here, here's Newfoundland, the other side of the wind field, the Azores down this way, and then we got Greenland way up there, and really pretty huge storm. And that was the wind field, what it did over the ocean. And just to give you a perspective of how huge and powerful these systems are, this is that storm. This is Gonzalo that eventually got to Bermuda. So this has got a huge effect, and you can see that even more so when you look at the wave field. This is how it came together, and you can see Gonzalo down in the lower left-hand corner, the wave field surrounding that storm. So these mid-latitude low-pressure systems are hugely destructive, and they move a lot of ocean. Then we had another storm in the Azores travel 500 miles to the west. I've seen them retrograde, but to actually travel 500 miles in a retrograde, that's crazy. Then, of course, we just had a storm last week, right? Persist for 3 or 4 days. Well, what happened there? It was more of these jet stream annex that produced this. So we had this big, long fetch off to the east, which is where we got 24-foot wave heights from. It didn't last a whole long time, but it was 4 or 5 hours. And this storm formed and stalled, and the reason that happened is because we had this dip in the jet stream, so the storm formed here. Well, now watch what happened to the jet. It kinks up and fades away and leaves the storm behind. And here's the jet running up here, and the storm has got nothing to push it along. And then later, a finger of the jet broke off, came down, picked it up, and pushed it out. But that's why it stalled, because of this undulating jet stream. So, in a warming climate, it stores more heat energy in the ocean, more water vapor in the air. Storms have more things to work with. We have this wavy polar jet stream, which is going to be part of the norm in a warming climate. And when this wavy polar jet digs deep to the south, it's going to tap into tropical air and the Gulf Stream and provide that contrast with that Arctic cold. And it's also going to go far enough south that it's going to actually latch onto that subtropical jet for even more moisture. And when you have that big dip in the jet, that's where we're going to get our storms. So weather systems can also slow down in this scenario and travel backwards like Sandy did. And, all in all, it's my opinion, and a lot of other people too, that, nature just increased our odds of rolling us more big storms. So let's build a storm. So picture early March in New England. We got frost in the ground's kind of bare, so there's not much snow cover. You get any rain on this type of ground, it's just going to run off. And then we've got, daytime highs in the 30s, nighttime in the 20s. It's not a good time to be without power. And I've been without power 4 times in the last 7 years in West Newbury for downed trees during late February, early March storms. And it wasn't just out for a day, be out for 4 or 5 days, and you just watch the temperature of the house go down and down and down. And, people up the street have power, but there's a cluster of 5 houses in your neighborhood that all of a sudden doesn't, and nobody can tell you when it's going to come back on. So it's kind of nerve-wracking to be in that situation. And then there were other people during some of those ice storms, 4 weeks, no power. All the pipes went in the house. Totally destructive if you have a business or a house, and you lose power in the middle of winter. So we also have our meteorologists buzzing about this big storm that's going to form out off of the coastline and track back towards New England. And there's quite a cast of characters in the meteorological field and broadcast meteorology. This guy's pretty good, Greg the weatherman. I don't know if you watch Family Guy, but this guy's pretty funny. And then lastly, there's always one guy who's got a different forecast from everybody else. And if you laughed at that, it reveals how old you are. cartoon from my childhood. I liked it. And then there's these guys. They show up for every storm, even on Plum Island. Anyway, so here we have our jet stream. We've got the polar jet being pushed south by a big cold high pressure cell. It latches onto that subtropical jet, and where the jets are phasing, we're going to get some divergence in the upper atmosphere and extreme low pressure right at the surface. And if we draw a weather map and the big picture of what this looks like, so here we have our high pressure cell pushing off the coast. We've got blocking high pressure to the north like we had with Sandy and actually with Saturn, this March storm that took all the houses. And we're going to also have a storm out here near the Azores, because that's what happened with Sandy and also during the March storm. And when we draw in the wind and the wave fields, which are going to be colored in yellow, those are the wind and wave vectors that are going to push waves and water towards our shore. So what's going to happen is you're going to have waves generated by this pressure gradient here coming into the wind field of our developing storm, and that storm is going to move back northwest and make a landfall along eastern Long Island for a bad case scenario. So what would happen during the first day? So the storm's still offshore. We're basically anticipating this thing coming, and there it is sitting out there, moving slowly to the northwest. Winds are starting to pick up from the northeast, 25 to 35 miles an hour, and then they start to veer into the east a bit more as the storm approaches, and we start to get these spiral bands of rain and clouds spinning in, and it starts to rain a cold rain. Of course, we're going to have all the news trucks there because this is really well forecast. One thing with these low pressure systems is they're much easier to forecast than a hurricane. So many factors need to come together for a hurricane to form, but these lows, I see it in the weather models all the time. When they start to agree 7 days out and they're using different algorithms to come to the conclusion, then I start believing something's going to happen. So this is well forecast, and we'd get a lot of media attention. And we'd have our constables interviewed by the Weather Channel. And then, of course, you know, all the notoriety and stuff, people are going to come down to the beach, they're going to start taking pictures, they want to see what this is all about. And by the end of that first day, we would see a 10 to 15 foot sea with about an 8 to 10 second period. And when I talk about wave periods, it refers to how far apart the waves are spaced. So if you're a weather buoy, a wave passes underneath you, you count off 8 seconds till the next wave shows up, that's an 8-second wave. Now as wave period goes up, so does the wave energy. On this size wave, we would expect 2,500 kilojoules per meter. Now that's a weird number and also a weird unit of measure. I have no idea what that means, but I know what it means when somebody says, well, this is what a 200 kilojoule wave feels like. Then I know what that is, and I do. So let me just explain it to you and put it into some perspective. You go to the beach, you got knee-high waves breaking against you. That's about a 50 kilojoule wave. If you're down the beach and it's maybe waist to chest high and you're standing in the shore break of Plum Island and it whacks you in the chest and you fall on your back, that's a 250 kilojoule wave. So 2,500 is 100 times more powerful than that. And this is the weird thing with waves, is that wave power doesn't like double, like an 8-foot wave isn't twice as powerful as a 4-foot wave. It's like 3 or 4 times as powerful. So when wave height goes up with period, things get pretty exciting. With the Merrimack River and all these estuaries, a lot of organic material in the water, and we get sea foam developing, and that comes in and gets blown in and blows all over the place, attaches itself to things. It's also full of sand, if you ever picked it up. And during this first day, we'd expect our 9-foot tide that we theorized to be bumped up a foot due to all the wave activity and the wind pushing things in towards shore. So, the other thing that happens in our area, which is unique to us, is we've got this Merrimack River inlet here, and we've got this constricting river jetty system that forces what used to be a river that was about this wide down to a river that's about that wide. So when the ocean rises up higher than the river and keeps pumping water in with waves, the river doesn't have anywhere to go. but behind Plum Island, behind Salisbury Beach, and it just keeps flowing back there and just keeps backing up because the ocean won't let it back out. So we get flooding from behind on barrier beaches here in our area. And if you look at this, this is from the March storm where all the houses fell in on Plum Island. If you recall, there wasn't any rain, there was barely any snow. It was just the ocean holding the river in. So all of this flooding is just from what's washing down the river without any rain on it. So you can see here that an extra foot of water here would have made a huge difference to this barrier beach. It's all pretty flat and low-lying. Marsh is entirely covered just with pure river water. Well, actually, this is ocean water that poured in at low tide and it just sat there when the tide came back in. And then, of course, the nose of the basin there, it's where the river mouth used to be, so that's always a little bit disconcerting, looking at that from that perspective. And then this just gives you a perspective of what those waves looked like back in March. I mean, here are our houses, right? This is a 40-foot house. That wave's breaking out there about a half mile to a mile offshore. And so that wave ought to look smaller, right? And then, of course, this water is going to back up the river. It's just going to keep stacking up. So along Joppa, we're going to see some things getting wet. And our emergency management people are probably also going to be out there working that. Day 2, we start to get winds of change. Now, if you go out in one of those storms in England where I showed you the waves from, in a 100-mile-an-hour wind with an umbrella, this is what happens. And that's maybe where they get the idea of Mary Poppins from. See, I thought I'd introduce a little bit of humor into this dire presentation. So there's our storm, parked just southeast and really spooled up. And if you saw pictures of Nemo, which was further offshore in 2012, that produced those 36-foot waves, that storm looked like this one. So the seas are ramping up. Now they're 10 feet higher with an even longer period from the east-southeast. The offshore waves are coming in from that other storm as well. They're entering the wind field, getting re-energized and made bigger. And our wave power now goes up to 10,000 kilojoules per meter. And that's what it was in March for that storm that took all the homes. This is only day 2. But the surge rises another 2 feet and makes for a 12-foot tide, which is pretty darn high to have this kind of wave energy coming in. This is actual footage from March of the Salisbury beach dune getting hammered during that March storm. And what would happen is we'd start to get splashover and washover at high tide in low-lying parts of both barrier beaches. And what would happen is sand would get pushed from the beach through low-lying spots onto the roads in the back. They're called overwash fans. And then the waters would start to creep across the access ways to the beaches, and it'd be kind of tough to drive a vehicle through there. And then homes on Plum Island and Salisbury Beach would start to get inundated from the rear as the river keeps stacking that water up, and it can't flow back out. Inland, because it's raining, we got a tremendous amount of runoff. This is a picture of the powwow from the Mother's Day storm, but this is probably what it would look like should this happen. And we'd get flooding along our riverfront as the Merrimack backs up, and the wind would start blowing some of that water and waves over the waterfront. And the winds are gusting 45 to 55 with some 65 to 75 mile-an-hour gusts. And we start to see some trees come down. And then we start to get some sporadic power outages here and there related to falling trees. Now on day 3, we would expect peak intensity of this storm. And what happens on day 3, and this is an actual satellite photo of the blizzard of '78, which was a retrograding storm. And that was heading foreshore, but actually stopped before it got there, didn't actually make landfall, and then turned back off and went off to the east and dissipated. Could have been much more devastating if it actually made landfall, but it was bad enough as it was. But that's roughly what we think it would look like. And this would be the wave field Here we have the dying storm out off near the Azores. Its waves have already been entered into this wind field, re-energized, and we get some big near-shore wave heights. Now this here is a very interesting model picture. This shows our landfall, eastern Long Island, with the storm center moving inland. And here is what I talk about being the bad side of the storm for a storm that moves in off the ocean towards us. This is a model of what Sandy would have done if it landed here instead of down here. Not a lot of distance. And if you look here, we've got this big swath of huge wave heights coming in through that northeast channel. It's 30 feet inside Ipswich Bay, and this model historically underestimates storm wave heights by about 8 feet. So that's a pretty bad situation for a storm to approach like that. So what's that look like? Well, this is what it looked like for Sandy. Waves were huge. So 20 to 30,000 kilojoules per meter, 2 to 3 times that of the March storm is what that wave energy would be. And remember, a 250 kilojoule wave will knock you over, so what would 30,000 do? So in a situation like this, you know, houses are immediately on the shore, especially along Plum Island where the seawall was recently built. That's not a mortared wall, it's just laying there on the sand. There is some footing to it, but this type of wave energy would take those stones and start moving around, and in some cases, because there's so many different sized rocks in that wall, a lot of them would probably get hurtled over the dune and into the homes and onto the streets behind it like it did in the Azores. And in this scenario, probably a good portion of those homes would fail. We start getting a lot of overwash at this point. There might be some breaches that start to form. Basically, the water's just getting pushed up over the dune by the waves, and it's running down the backside back into the marsh and carrying a whole bunch of sand with it. These are pictures of places where this has actually happened, so you can kind of get an idea of what happens here. I mean, look at the mounds of sand that have been plowed out of the street because they're trying to get this water to flow back into a marsh behind this barrier beach. Inland, it's a little bit colder as elevation rises, and we start to get ice inland, and trees start to come down. And this is what it does with all our power lines in March. And this is when all the lights go out. And you don't see those guys on the Weather Channel because you can't watch them. But if Sandy is any kind of a record of what's going to happen, you know, because it's all well broadcast, you're going to have fleets of electrical linesmen staging in Ohio and North Carolina waiting for this storm to end, because they're all going to be traveling to the Northeast and working feverishly in really cold weather to put electrical lines back up and poles back up. But they got to wait till the storm's over. And you're going to have, everybody's going to be out of power. This is a New England-wide problem at this point. I mean, you're going to have Maine, New Hampshire, probably parts of Vermont, certainly all of Massachusetts, Connecticut, and Rhode Island with no power. And it took most people from Sandy 1 to 2 weeks to get their power back, and then there were places, pockets, 3-4 weeks. So if you have a business, or you got a house in March, I mean, that's a heck of a long time to be without power. What are you going to do? This is a good time to just talk a second about an interesting concept. What about if we took all those electrical poles and put them underground and made sidewalks where we can actually walk and bike on? And then when a storm comes through, we're not having everything fall down and take everything out. And the other nice thing is when you run all these utilities under sidewalks and underneath crosswalks, if there's ever an issue, you lift up a piece of concrete section and fix the problem, put it back down, and the road is done. None of this digging up a septic line every 25 feet when somebody has a problem just after you pave the road. This is a much better way to do it. And you can actually have people walking around in there, and it's all nice and orderly, instead of this type of situation, which is what we primarily do now. We dig pits, we fill it in with gravel, we make everything inaccessible, and we disrupt an entire neighborhood, a bunch of businesses and streets. Anyway, that's a sidebar. So anyway, torrential rains, filling the Merrimack. It's getting even higher. The causeways are impassable at this point, and we would expect Plum Island Point to look something like that. Rings Island would flood and become isolated, actually. And we all saw what this happened during the Mother's Day storm in Newburyport along the waterfront. And you got flooding backing all the way up to the Chain Bridge, and anything that's low there, close to the water, is certainly going to be pretty vulnerable. And one of the things that you got to consider is we've got a water treatment plant up in Maudsley that took on some water back in the Mother's Day storm. Certainly going to take on water in this one. And the thing is, to contaminate a water supply, you need about 1 millimeter of water. When you fill up a bathtub, you can fill it up, and once it hits that tipping point, that 1 millimeter, it's all over the floor. It's the same thing with this. I mean, you don't need a whole lot to contaminate a water supply and also paralyze a septic plant. And you got to remember, everybody's sitting at home, and what are they doing? If the power was still on, they'd be watching TV, eating, drinking, and going to the bathroom. So where's all this water going to go? I mean, especially if the water level at the septic plant is higher than the discharge, and you get all this hydraulic pressure being forced backwards up the system. It's really something to think about. And then, of course, we know about our issues in the industrial park. That gets pretty wet because the Little River backs up, because if the Little River can't discharge into the marsh, it's got to discharge somewhere else, and it's going to discharge into the industrial park. And then, the Merrimack River is just pumping that water down because it's raining all the way up to Wolfboro, and it's all coming down every tributary, and is going to stress every dam, and that water's got nowhere to go but stop in Newburyport. Amesbury has similar issues with the powwow and all that infrastructure with that river running under the center of town. You got to wonder what's going on underneath the center of town there. And there's going to be some flooding there as the back river overflows, and there's going to be roads that get washed out. There's going to be new streams that form that never used to be there before. So day 4 is the aftermath. And this is when we figure out what the heck happened here. So this storm travels along the jet stream up into the Canadian border and spins itself out up in upper New York State, which is basically what Sandy did. We still got a bunch of swell coming in for several days, probably 3 to 4 days, till that wave train runs out. Still pretty significant, 15 to 20 feet, but tapering off instead of getting bigger. And the marshes start to come back as the waters recede. And we're going to find, lots of debris moved around as a result of this storm. But then help starts to show up. And, we're certainly going to have the National Guard here. And then we go out and assess our damages. So this is pretty National Geographic, right? I mean, this is what we'd see in the reservation. You'd see that the ocean basically came up here, took the sand that used to be up front here and pushed it back over the marsh. And this is part of the process that happens in a rising sea level scenario where barrier islands start walking backwards, directed by the forces of waves. Because as waves can top a dune, it's all downhill to the marsh at that point. And so it's going to push the sand backwards because you get waves pushing that water and sand in, and then gravity takes over and keeps rolling it to the back shore. These are pictures of what happened during Sandy. So Long Island, Fire Island, places like that. And you can see these overwash fans of sand. This is a close-up shot here. This is about 15 feet thick of overwash sand. How many bulldozers would it take to build that pile in the time it took that storm to do it in one high tide? So when this happens in a populated area, it doesn't look so pretty because houses are standing in the way and nature doesn't really care. And so it ends up looking like Beirut or some sort of a war zone. And, when Sandy came in, it just took everything. Boardwalks, roads, utilities, foundations from houses, everything just went right down the street. And you can kind of see how deep the sand is around these cars. I mean, they had quite a mess to clean up down there, and they're still cleaning it up. So inland, we've got all this flood water that we got to wait to drain away. We're going to have cold people with no place to live, no heat, no electricity, no food. Certainly plenty of wildlife is going to suffer too. And it's just not going to be a happy situation to have this type of thing happen in March. But March is actually a big storm month, That's when some of those bigger storms have formed off of our coast. And you just got to have to hope that they keep forming east of us and not travel backwards. So you start drying out, start recovering cars that probably won't run anymore. And if you got a generator and a sump pump, you can start pumping yourself out. I bought a generator, by the way. I'm not going to be without power for 4 days again. And then there's going to be a lot of cleaning up. So how realistic is this? Let's take a look. Look at some of these storms by the numbers. So up across the left here, we get our 3 storms that plagued Europe. Really low central pressures, 927. Hercules was 944, and then Xaver, which was in December, was 962. Our storm, we put it at 950, which we chose Sandy, the perfect storm, and the blizzard of 78 as sort of our storm to work around. So we kind of picked a number that was sort of in the middle of those. These winds aren't really out of the ordinary, 50 to 60, 80 to 90 mile an hour gusts. Certainly a lot less than what was going on over in Europe, and even less than what was going on with the Northeast blizzard. Relative to wave heights, our wave heights are similar to what was going on in our New England storms, not as big as the European stuff. But the difference with our storm versus these others is that it retrograded in, it happened in March and it rained, and it was a slow-moving storm and it made landfall. And that is really the key difference between the perfect storm and the Northeast blizzard. They both retrograded, they headed in our direction, but they never made landfall. And so it actually looks fairly realistic as far as meteorology is concerned. So we did have a close call in March 2014. Again, nobody talked about it. But there was the storm. Again, it blew up right there, hard up against Nova Scotia, fortunately for us. Nice, big, intense wind field. You can see where all this wind energy is going right into Nova Scotia. And this is certainly what happened with the waves. So here's the storm center. Here's this big hook of, I don't know, probably 40, 50-foot waves heading up in that direction. And again, if this storm formed over here, 200 miles, then this would be coming into the Gulf of Maine. And that storm rotated around, and it moved off. It didn't stall. It just blew up, bombed out, made its angry ocean, and moved on. But there were some big wave heights in there. Fortunately, and then, by the way, surf was up down in Puerto Rico. But this is what Nova Scotia got for waves off of that storm. And again, it's a rocky coast. Nobody's got a house sitting down here where this photographer is. A few barges broke loose and washed up in places, and they got down limbs and trees, and they got a lot of snow out of it. But they're a hardy bunch up there, and they survived okay. So just to kind of wrap things up here, so we've got people that don't believe that any of this is happening, and they're experts. But the reality of it is, if you look at the science, it's really not really that much of an argument. So, I always tell people, you talk about climate change, they ask me what I do, and they go, oh, you really believe in that? And I'm like, it's not a religion. So you either look at the science, you analyze it, and make a judgment about it, or you ignore it, and the evidence is really pretty overwhelming. And the thing is, this whole thing it's a huge problem for sure, but there's a ton of opportunity within climate change. I mean, there's planning jobs. What are we going to do with our communities? We need planners, we need engineers, we need coastal geologists, we need hydrologists, we need people that are grant writers, we need people to figure out how we're going to do all this stuff. So there's a lot of opportunity just in the adaptation side of it and mitigating our damages. And then certainly there's going to be a lot of work in recovery if something happens, because nobody's ready for this. The other side of it is you got the whole green energy industry. Why don't you take some of that money away from big oil and develop something that we can all use instead of letting them keep it all? And I mean, you know, I always shake my head. I mean, we buy all this oil from the Middle East. It's sort of like going into a store where somebody makes a bad gesture to you every time you walk in and you hand them $20. Why would you go back, you know? We give them money so they can terrorize us. It makes no sense. So anyway, if all of these peer-reviewed studies are wrong, what's the worst that could happen if we address this problem? Come on. Well, you basically create a better world for nothing. There's such a huge downside to addressing climate change. And, you know, if there's any reason to do something about this, the reason would be this. Come on. You know, we all have kids, right? And we have grandchildren. And, you know, I grew up, I never had any dark cloud like this hanging over my head. No dark cloud of a warming climate, species dying off, ecosystems becoming disrupted, food supplies being threatened, new diseases coming out. None of that stuff was going on. I didn't have to think about that. But my son has got to think about that, and so do his kids. And, you know, he's not a little kid anymore. He's a teenager. But he's going to have children, and they're going to be dealing with the thick of this stuff. So we got to start doing something now, because they're going to look back and they're going to say, what the heck were they doing back then? Oh, well, they were just trying to decide if it was really happening or not. Well, the data's there. It said it did happen. Well, they didn't believe it. So that basically concludes my presentation, and I hope you enjoyed that, and I hope I created a sense of urgency. So what I'd like to do is we're going to hold off on questions till the end, and we've got a couple of shorter presentations for you coming up from Jack Clark is going to be our next speaker. He's with Mass Audubon. And then we're going to follow his presentation with Mary Ann Clancy, former mayor, and with the Chamber of Commerce about a survey they did on climate change and sea level rise. So I'm just going to cue up Jack's presentation, and I'm going to turn the reins over to Jack.